All right, let's look at an intro to acids and bases. Hopefully you know a lot of this already. This tends to follow our book, but it's not going to precisely follow the book, but it's pretty close. Acids. Here's some examples: HCl, HBr, HI, H2SO4, HNO3, HClO4. Let's play a little Sesame Street. What do these acids all have in common? That's right, these are our common strong acids. These are our 6 strong acids. Note, there actually are more than 6 strong acids. It's just we rarely ever see any of the others. In fact, you rarely deal with perchloric acid. And truthfully, you don't very much deal with hydroiodic acid. HCl all the time. HBr, yeah, sometimes. HI, not too much. H2SO4 all the time. HNO3 all the time. HClO4, not that much. The problem with HClO4, it's kind of a nasty acid. It's not good for you. And the other problem is when you neutralize this perchloric acid, you get perchlorate salts, and some of your perchlorate salts are shock-sensitive explosives. So it would not be nice to pour off your liquid, have this solid, shake it up, and have your glassware explode on you. So we don't deal with perchloric acid unless we have to. However, it has some very good uses. All right, these are our strong acids. We have a whole bunch of weak acids. Note, most acids are weak acids. And a lot of the weak acids, not all, but a lot of the weak acids have this carboxyl group, this hydrogen bonded to oxygen. That oxygen is bonded to a carbon that is double bonded to an oxygen. We call this carbon double bond oxygen a carbonyl group. So our carboxyl group is an OH, a hydroxyl group, bonded to a carbonyl group. And this carboxyl group is very common in weak acids. Whatever is attached to that carboxyl group changes what the acid is. Here, if there's a CH3 bonded to it, that's acetic acid. It's a weak acid. And this carboxyl group, when we look at, oh, this is an acid because it's got the carboxyl group on it, we call it a carboxylic acid. Things about acids: they turn blue litmus paper red, and they taste sour. Now, don't go tasting your acids in the lab. You know, you taste hydrochloric acid. Oh, that's sour. Now it's burning my tongue out of my mouth. So don't do that. However, you have tasted sour acids. Vitamin C, ascorbic acid, citric acid are sour. Lemons are sour. Grapefruits tend to be sour because of ascorbic and citric acids. Oranges would be sour, and if they're not ripe, they're sour. It's just oranges have a whole lot more sugar in there, so you don't quite taste the sour taste as much because of the sugar. But if you have candies like Sour Patch Kids and Sweet Tarts and stuff like that, if you look in the ingredients, you'll find like ascorbic acid and citric acid. It's that acid taste, that acid that gives them that sour taste. Bases. Common bases, strong bases: sodium hydroxide, lithium hydroxide, potassium hydroxide, barium hydroxide. These are our common strong bases. And ammonia is a weak base. Some things about bases: they turn red litmus paper blue. Bases tend to be slippery. Soap is slippery. Soap is actually a little basic. And bases taste bitter. Don't taste your bases in the lab. Don't do that. Oh, I'm going to taste my sodium hydroxide. Heck, it's bitter, and now my tongue is burning out of my mouth, and then that's bad. So don't taste anything in the lab. They just taste bitter. Prime example: alkaloids are the bases that you find in plants. And it turns out most people don't like bitter taste because a lot of alkaloids, these plant bases, are poisonous for you. Now that they might affect, or they affect you in ways that too much is poisonous. Nicotine is a alkaloid, and yeah, you find it in smoke, and it makes you a little jittery, but too much will kill you. Caffeine is an alkaloid. Too much of that will kill you. So yeah, they are plant-based bases or alkaloids. They taste bitter. Most animals do not like bitter taste. It's just what we have evolutionarily come to find. We don't like bitter taste, so we tend to not eat bitter plants, and bitter plants can be poisonous, so we tend to live longer when we don't do that. All right. So, before we move on, these are our common strong acids. Here's a weak acid. Here's our common strong bases. Here's a weak base. Do you recall the definition of strong acids versus weak acids? That's right. Strong acids dissociate 100% in water. Strong bases dissociate 100% in water. Weak acids, weak bases do not dissociate 100%, which means weak acids and weak bases, in order to understand them, you need to understand equilibrium. All right, equilibrium. Yay. I can't wait to get back into that. All right, continuing on with definitions of acids and bases. And first along was Arrhenius. Arrhenius, very, very smart, a true genius, a true jerk, but sometimes geniuses can be jerk. They think highly of themselves. Anyway, Arrhenius, he defined an acid as a substance that produces H plus protons in water, and a base, a substance that produces hydroxide in water. This should be review of Gen Chem 1. And so Arrhenius would say, oh, if HCl is aqueous, it'll dissociate 100% into H plus aqueous and Cl minus aqueous, aqueous proton and aqueous chloride ions. A strong base, sodium hydroxide, that's HCl strong acid, dissociates 100%. Sodium hydroxide, a strong base, dissociates 100% in water to Na plus aqueous and OH minus aqueous. And Arrhenius would say a neutralization reaction, H plus OH minus, react to form water. Cool. And then along come Bronsted and Lowry, and frankly, they were just say, hey, can we get rid of the whole water issue here? Can we have a definition of acids and bases where we don't have to have water? And Bronsted-Lowry is like, okay, we came up with this. It turns out because you don't deal with water, even though it can, this is more widely applicable. It's a more general rule. Any acid that is classified as Arrhenius acid is also a Bronsted-Lowry acid. Any base that is classified as Arrhenius base is also a Bronsted-Lowry base. However, you will find, especially when you go to organic chemistry, that Bronsted-Lowry acids and bases might not be Arrhenius acids and bases all the time. It's a more general definition, and we tend to like it better. With Bronsted-Lowry acids and bases, you have to put the water in there. Any reaction that is a Bronsted-Lowry acid-base reaction, you need an acid and a base. So while Arrhenius would write HCl as HCl aqueous goes to H plus aqueous plus Cl minus aqueous, Bronsted-Lowry would say HCl aqueous plus H2O liquid goes to H3O plus aqueous plus Cl minus aqueous. Okay. So note H3O plus aqueous and H plus aqueous are the same thing. A proton is the same thing as a hydronium ion. They're just two different ways to write a proton dissolved in water, an aqueous proton. You can write it as H plus aqueous or H3O plus aqueous. They mean the same thing. The only difference is if you write your acids the way Arrhenius would and you don't have water here, you write H plus. If you write your acid reactions the way Bronsted-Lowry do, and there is water there, you write H3O plus. Something also to note, Bronsted-Lowry does very nicely with weak bases. NH3 aqueous plus H2O liquid is in equilibrium with NH4 plus aqueous plus OH minus. You have your base and you have your acid in there, and note you generate OH minus. Arrhenius, sometimes some of these weak bases, ammonia type bases, just don't work well for Arrhenius equation. And by the other thing too is strong bases like sodium hydroxide don't really work very well doing Bronsted-Lowry. So if you're writing an acid reaction, an acid dissociating water, it doesn't matter too much if you use Arrhenius or Bronsted-Lowry. If you're writing strong base dissociation, you need to use Arrhenius. If you're writing weak base reaction, you need to use Bronsted-Lowry. All right. But the Bronsted-Lowry definition, an acid is a proton donor, donates protons. A base is a proton acceptor. HCl is an acid because it donated this H to the water. Water is a base because it accepted the proton to become H3O plus. H2O accepted a proton to become H3O plus, so water is the base. HCl donated that proton to the water, so HCl is the acid. And if we look over here, we have an acid and a base, and which is the acid, which is the base? Got NH3 and water. Well, the question is, what accepted the proton, what donated it? We look, we have NH3 over here, we have NH4 over here, so NH3 had to accept a proton to become NH4 plus. Proton acceptor, base. NH3 is the base because it accepted the proton. Water is the acid because water donated the proton. Note, in this reaction, water was the base. In this reaction, water was the acid. And there are several molecules that will do this. They are fine working as acids. They are fine working as bases also. Now, the other thing with Bronsted-Lowry is that you must have acid-base pairs, conjugate acid-base pairs when you are dealing with Bronsted-Lowry acids and bases. So, in the reaction we had before, an acid plus a base water, HCl is the acid, it donated the proton, and in doing so, it became the conjugate base, Cl-. Water was the base, it accepted the proton, definition of base, proton acceptor, it accepted the base and became the conjugate acid, H3O+. All right. The bases, we do the same thing. Here's NH3 aqueous plus H2O liquid goes to NH4 plus aqueous plus OH minus aqueous. NH3 becomes NH4 plus. It accepted a proton, so it's the base. So NH3 is the base and accepted the proton to become the conjugate acid, NH4 plus. Water is the acid, the proton donor, and it, after donating the proton, it becomes the conjugate base, OH minus. And note, whenever you write Bronsted-Lowry reactions, the reactants are always the acid and the base. The products are always the conjugate acid and the conjugate base. The conjugates are always on the product side. Note, NH3 plus H2O, this reaction is a weak, NH3 is a weak base, which means this is equilibrium, so we could have written the reverse reaction. If you write the reverse reaction, NH4 plus OH minus in equilibrium with NH3 aqueous plus H2O liquid, since it's a reverse reaction, now NH4 plus is the acid and OH minus is the base. How do we know NH4 plus is the acid? Because it donates the proton to water. And after it donated the proton, it's got one less proton. It is now NH3 aqueous. All right, some other definitions along these lines. Towards the end of the chapter, we're going to have another definition of acids and bases. But other words we need to know the definition of. Amphoteric can act as an acid as a base. That's our water there. Water was amphoteric because it could act as an acid in a reaction. It could act as a base in a different reaction. Amphoteric can accept protons, can donate protons. The acids we've been looking at, like HCl, are monoprotic. Monoprotic, one proton acid. It has one proton, it can donate. You also have diprotic acid, H2SO4. Both of these hydrogens, both these protons, are ionizable. They both can leave. H2SO4 can give up one proton, and then HSO4 minus, the conjugate base could act as an acid and give up another proton. It's diprotic. We already talked about our strong acids and weak acids. Strong acids associate 100%, weak acids not 100%. So we have equilibrium. All right. And for a weak acid, since we have equilibrium, and I'm writing it the way Arrhenius would, we're going to find out that it's just less to write a lot. I'm going to abbreviate my weak acid as HA. So HA, my weak acid, is in equilibrium with H plus plus A minus. It's an equilibrium, so it must have an equilibrium constant. And we call that equilibrium constant the acid dissociation constant or acid ionization constant, Ka. Ka is the equilibrium constant for an acid dissociating in water, and it's concentration of H plus times concentration of A minus divided by the concentration of HA. So any acid in water, its Ka is just this equilibrium where it dissociates into protons, the conjugate base, and it has a Ka value that can be measured. Okay. Note, this is how Arrhenius would write this, and this is the Ka equation you get with Arrhenius. What if you wrote the HA, this weak acid, dissociating as Bronsted and Lowry would, where you've got water in there? Well, we know HA plus H2O liquid goes to H3O plus A minus. Note, this Ka value would be H3O plus times concentration of A minus divided by the concentration of HA, because water is a pure liquid, or the liquid, it's not in there. You don't put liquids in the equilibrium constant expression. So the only difference between these two Kas for this weak acid HA is this says H plus here, and this is H3O plus. But since we know H plus equals H3O plus, that means these two are the same. It doesn't matter if you write it as Arrhenius would, or if you write it as Bronsted-Lowry would, you get the same Ka value, you get the same Ka expression, because H3O plus is the same as H plus. All right. So, in our next video, we will look at what happens when you mix water with water. Technically, you don't have to mix it. It's already mixed. But we'll look at the autoionization of water.